Now we will continue the conic sections and special curves in which methods of constructing conics learning now. So in continuation, now we will discuss involutes and spirals. So first we will go to involutes. Involute is the locus of a point on a string as the string unwinds itself from a line or polygon. These involutes are three methods. First method, inversion of line. Now second method, involute of triangle, and third method, involute of circle. So in this way, the involute of methods are available. Now let us go to involutes definition and then first method.
Involute. An involute is the locus of a point on a string. As the string is divided into someone else involute of the line. Try number 23. Draw the involute of the line for 20 centimeters for 2.5 circles.
Now let us observe involute of line in this method.
Every particular is 20 centimeters length. With center AB is equal to R1. Draw a semicircle AC. Now, the center of AC is equal to R1. Draw a semicircle. With the center and radius BC, that's equal to R3, draw a semicircle.
That is, its center A, one semicircle, its center B, D to A, one semicircle, its center C, one semicircle. So once again,
With
finally, we conclude that in this involute of line, by using the centers of point A and point B, alternatively we can draw the involute of a line. Now, in second method, involute of triangle. Once again, third method. In this third method, involution of triangle, involute of circle. Problem number 25. Draw the involute of a circle. Diameter 50 mm. Also draw tangents and normal at any point on the curve. Draw the circle of given 50 mm diameter. Divide the circle into 12 equal divisions. If you want to more also, you can make the divisions for accuracy. Now draw the tangent to all the division points. Now measure PQ equal to equal to the circumference of the circle and divide it into 12 equal parts. On tangent drawn at point 1, step of 1p1 is equal to p11, and on the tangent drawn at p2, step of 2p2 is equal to p21. Similarly, obtain the points P2, P3, P4 and draw a smooth curve passing through these points. Draw tangents to involute, mark the point A at which the tangent is to be drawn. Connect AO and mark the point C as the midpoint of AO. Center C and radius AC. Describe semicircle which cuts the base circle with center O at B. It is for previous drawn AO with center C and radius AC. Describe a semicircle which cuts the base circle with center O at B. Connect AB which is a normal. Draw tangent by drawing a line perpendicular to AB through point A. This is the first method of involute of circle. Second method. These are all the involution of circle methods. circle is the locus of point which moves around circle center called pole while moving away from the center. Archimedeal spiral. It is defined as locus of point which moves with uniform linear velocity along the radius vector, while the radius vector itself rotates with uniform angular velocity. Now in this problem 26, construct a Archimedeal spiral for one convolution. The initial and final radius vector are 25 mm and 100 mm respectively. Draw tangent and a normal to spiral at a point 50 mm from the pole. Now let us draw. With the pole O as center and radius OB equal to final radius vector 100 mm, draw a circle. After drawing a circle, mark OA equal to the initial radius vector 25 mm. Then divide AB into 12 equal parts. That is 100 mm. And divide the circle into 12 equal parts. With center O as draw concentric circle arcs with radii O1, O2, O3 and so on to intersect the corresponding radial lines O1 dash, O2 dash, O3 dash and so on at P1, P2, P3. Once again with center O, draw concentric arcs with radii O1, O2, O3 etc. so as to intersect the corresponding radial lines to O1 dash, O2 dash, O3 dash, etc. at P1, P2, P3. Now draw a smooth curve passing through these points, that is P1, P2, P3 and so on to get the required Archimedean spiral. Now draw tangent to Archimedean spiral with the pole O as center and 50 mm as radius. Draw an arc to cut the spiral at P. Now connect PO and measure angle POA is equal to 120 degrees. Draw OQ which is perpendicular to OP. The polar equation R is equal to C plus A theta. In this, theta is 120 degrees, R is 50 mm, C is 25 mm. From the given data, when theta is equal to 120 degrees, the radial value of theta is equal to 120 by into pi by 180, which is equal to 2.1 mm. Now R is equal to C plus A theta, which implies A is equal to R minus C by theta. Value in radius, which implies 50 minus 25 by 2.1. After simplification, get 11.9. Now we will observe keenly. Measure OC is equal to A, which is equal to 11.9 mm on OQ. Now connect PC, and this is a normal. Draw PQ tangent perpendicular to the normal PC. Once again, with the center O as circle, center O as center and radius OB equal to final radius vector is 100 mm. Draw a circle. With this, mark OA is equal to initial radius vector 25 mm. Divide AB equal parts. It's 12 parts. Now the divide circle into 12 equal parts. First you divide OB AB into 12 parts and then draw a circle OB. Then that circle also will be divided into 12 equal parts. With the center O as, draw concentric arcs with the radii O1, O2, O3 and so on to intersect the corresponding radial lines O1 dash, O2 dash, O3 dash and so on at P1, P2, P3. Now I draw a smooth curve passing through these points to get the required Archimedean spiral. Now draw the tangents to Archimedean spiral with all the O as center and 50 mm as radius. Draw an arc to cut the spiral at P. Connect PO and measure angle POE is equal to 120 degrees. Now draw OQ, which is perpendicular to OP. Then the polar equation R is equal to C plus OA theta, where theta is equal to 120 degrees, R is 50 mm, C is 25 mm. When theta is equal to 120 degrees, the radial value of theta is equal to 120 into I by 180, which is in measured radius is equal to 2.1 mm. Now R is equal to C plus A theta, which implies A is equal to R minus C by theta, which is the value in radians. By substituting R, we get 50 minus 25 by 2.1, which is equal to 11.9. Measure OC is equal to A is equal to 11.9 mm on OQ. Now connect PC, and this is a normal. Draw P through tangent perpendicular to the normal PC. Now we will study cycloidal curves. Cycloidal curves are formed by a point on circumference of circle rolling upon a line or another circle. The rolling circle is generating circle. The line on which generating circle rolls on called baseline. The circle on which the generating circle rolls is called directing or base circle. Now define cycloid. Cycloid is a curve traced by a point on the circumference of circle which rolls without slipping along a line. These are cycloid curves are cycloid, epicycloid, hypocycloids. Now we will go to individuals of each. In this cycloid, once again define the cycloid. Cycloid curves are formed by a point on which circumference of the circle rolling upon a line or another circle. The rolling circle is a generating circle. The line on which generating circle rolls is called baseline. The circle on which the generating circles are rolls is called directing or base circle. Now define cycloid. Cycloid is a curve traced by point on the circumference of circle which rolls without slipping along a line. A circle of 60 mm diameter rolls along a circle line. A point on the circumference of circle is in contact with the line in the beginning and after one complete revolution. Draw the cycloidal path of point, draw tangent and normal at any point on the curve. With the pole O as center and radius OB equal to final radius vector 100 mm, draw a circle. To calculate the circumference of rolling circle is equal to pi d is equal to pi d is here 60. Is pi 60. Draw a line PQ equal to the circumference of rolling circle. Draw the rolling circle with O as center and radius R is equal to 30 mm and touching the line PQ at P. Now the P is a common point lying on the circle as well as on the line PQ. Now divide the circle into 12 equal parts and name the points in the counterclockwise direction as 1, 2, 3 and so on. Now you imagine when the rolling of the circle takes place, then the numbers 1, 2, 3, 4, 5, 6 etc. will move over that. Now draw the horizontal lines 1, 2, 3 etc. in the circle and extend it as shown. Now divide PQ into same number of equal parts and name the points 1 dash, 2 dash, 3 dash etc. Now at points 1 dash, 2 dash, 3 dash etc. draw lines perpendicular to PQ to intersect the horizontal line drawn through O, called the locus of the centers respectively at C1, C2, C3 and so on. Now with center C1 and radius equal to rolling circle or OP, cut the horizontal line drawn through point 1 and 11 of circle and name it as P1. Similarly obtain P2, P3, P4 and so on. Now I draw P1 and finally to Q. This is the rolling circle path. Now this curve is required, cycloidal curve. The rolling path you can calculate the cycloidal curve. Tangent and normal. Let A be the point on the curve at which the tangent and normal are to be drawn. Its center A and radius R is equal to OP. Cut the line of locus of centers at C. From C, draw a perpendicular to PQ to get the point B. Connect AB and extend it, which will be normal. Through A, draw a line XY perpendicular to AB, get the required tangent. Here we will observe all circle, that is the rolling directions given and rolling circle is there. Now locus of the centers, cycloidal path, tangent, so normal. Now we will study again how it is happening. Once again, calculate the circumference of the rolling circle. Pi d is equal to 560. Draw a line PQ equal to the circumference of rolling circle. Now draw the rotating circle. Rolling circle with O as center and radius R is equal to 30 and touching the line PQ at P. Now P is a common point lying on the circle as well as on the line PQ. Divide the circle into 12 parts and save the points is in the counterclockwise direction as 1, 2, 3 and so on. Now draw the horizontal lines through 1, 2, 3 etc. in the circle and extend it as shown in figure. Now divide PQ also into same number of equal parts and name the points 1 dash, 2 dash, 3 dash etc. At points 1 dash, 2 dash, 3 dash etc. draw a line perpendicular to PQ to intersect the normal, the horizontal line drawn through called the locus of centers respectively at C1, C2 and so on. At C1, C2 are called locus of the centers. This center will not change, so that's why it's the middle of the same path. Now, with the center C1 and radius equal to rolling circle or OP, cut the horizontal line drawn through point 1 and 11 of the circle and name it as P1. Similarly, obtain P2, P3, P4 and so on up to P11. Draw smooth curve from P through P11 and finally to point Q. Now this curve is required cycloidal curve. Now tangent and normal. Let A be point on the curve at which the tangent and normal are to be drawn. Its center A and radius R is equal to OP. Cut the line of the locus of centers at C. From C, draw a perpendicular to PQ to get the line point B. Connect AB and extend it, which will be the normal. Now, through A, draw a line XY perpendicular to AB to get the required tangent. Now, we'll discuss epicycloid. Epicycloid are a curve traced by a point on the circumference of circle which rolls without slipping on the outside of another circle. Let us consider problem number 28. Draw a cycloid of circle 60 mm dia which rolls outside on another circle of 160 mm dia. Draw the curve for one revolution. Also draw a tangent and normal at any point on the curve. Now let be the R of the rolling circle, and R is capital R is radius of directing and base circle on which the rolling circle rolls. We have to calculate theta, the angle subtended by the base circle for one revolution of the rolling circle. Arc 2 pi r subtends an angle 360 degrees at O. Arc 2 pi r subtends an angle theta. Theta is equal to 2 pi r by capital 2 pi r into 360 degrees, which is equal to r into 360 by capital R, which is equal to 30 into 360 by 80, which is simplified as 155 degrees. Now, with any point O as center and the radius capital R is equal to radius of base circle 160 mm, draw an arc PQ which subtends an angle theta at the center. On OP to produce mark point C such that PC is equal to R in radius of rolling circle. Now with the center C and radius R equal to 30 mm, draw the rolling circle. With center C and radius R is equal to 30 mm, draw the rolling circle. Divide the rolling circle into 12 equal parts and name the division points as 1, 2, 3 and so on. The numbering is done in the anti-clockwise direction. With O as center, draw a number of concentric arcs passing through the division points 1, 2, 3, etc. Also with O as center and radius OC is equal to capital R to small r, draw the radius of center's arc. Divide arc PQ into 12 equal parts and name the divisions points as 1 dash, 2 dash and so on. Now join O1 dash, O2 dash, O3 dash and so on and produce them to cut the locus of the center's arc at C1, C2, C3 etc. Now the point P moves in the clockwise direction by 1/12 of revolution of the rolling circle and reaches point P1 which lies on the arc drawn through 1 and 11. The point P is always at distance r is equal to Cp from the centers C1, C2, C3, etc. Now draw an arc with O as a center and O11 as the radius passing through point 1. For finding out the point P1 with the new centers C1 and radius r is equal to Cp, the radius of the rolling circle, cut the arc drawn through the point 1 at P1. Draw an arc with O as center and O10 as radius passing through the point 2. Similarly with C2 as center, with the same radius and cut arc drawn point 2 at P2. Then obtain P3, P4 similarly. Draw a smooth curve through P, P1, P2, P4, etc. This is the required epicycloid. Now draw a tangent and normal to the epicycloid. Let A be the point on the curve at which tangent and normal to be drawn. With center A and radius r is equal to Cp, cut the locus of arc of centers at a point D. Connect DO which intersects the arc of base circle PQ at V. Now let us join AB the normal. Through A, draw a line perpendicular to AB to get the required tangent. Now hypocycloid. Hypocycloid is a curve traced by a point on the circumference of the circle. When it rolls without slipping on the inside of another base or directing circle. This we will learn through problem number 29. Draw a cycloid of circle 40 mm diameter for one revolution. Also draw a tangent and normal at a point on the curve. Solution. Calculation of theta and other procedures are similar to the epicycloid except that the rolling circle is rolling inside the base circle with the following changes. The naming of the points of the rolling circle is in the clockwise direction. The rolling direction of this circle is in the anti-clockwise direction. For the procedure, refer to the figure which is self-explanatory. Students can take this as an exercise. Now this is the completion of hypocycloid. This is the end of the cycloidal curves. So with this explanation, close this